Take a block of table salt, hit it with a hammer, and it shatters into thousands of sharp, rigid fragments. Do the exact same thing to a block of candle wax, and it barely reacts. It's simply dense, bending around the impact. Both of these materials are simply collections of atoms. The reason they react so differently to physical force comes down entirely to how they handle their electrons. In table salt, a metal and a nonmetal interact through an ionic bond. This is a transaction. One atom completely rips an electron away from the other, creating two oppositely charged particles that lock tightly together. Candle wax, made entirely of nonmetals, uses a covalent bond. Instead of one atom stealing a particle, the atoms overlap their outer shells and share their electrons to achieve a stable configuration. That single microscopic decision, to either steal an electron or share one, acts as the architectural blueprint determining every physical property a material possesses. To see exactly how this blueprint dictates physical reality, we can run these materials through a series of chemical stress tests, starting with blunt physical pressure. Because ionic compounds like sodium chloride are built from alternating positive and negative charges, they arrange themselves into a massive, highly organized grid known as a face-centered cubic lattice. In this specific architecture, known as a 6-to-6 coordination, every single positive sodium ion is perfectly surrounded by 6 negative chloride ions. When you apply physical stress to this lattice, you push the rigid layers of the grid out of alignment. By shifting just one row over, you suddenly force identical charges, positive against positive and negative against negative, to sit side by side. Since like charges repel, that forced proximity triggers a massive wave of electrostatic repulsion. The structure violently tears itself apart along that fault line. Covalent compounds, however, don't form infinite grids. They exist as discrete, independent molecules. When pressure hits them, those individual units slide past one another, allowing the material to bend and flex rather than shatter. Macroscopic brittleness is a symptom of extreme microscopic organization. The strict architectural rules holding the salt together are exactly what cause it to fail when the pressure shifts. Next, we test the thermal endurance of these bonds by applying extreme heat until the compounds melt. This table from our research outlines the melting and boiling points of several ionic compounds. Looking at the top row, we can see that turning solid sodium chloride into a liquid requires an immense temperature of 1074 degrees Kelvin. The adjacent column shows that boiling these compounds takes even more energy. This massive thermal resistance exists because ionic bonds are non-directional. The electrostatic attraction pulls equally from all three dimensions, creating a relentless grip on every atom in the grid. Covalent compounds operate differently. While the internal sharing of electrons makes the molecule itself highly stable, the attractive forces connecting one molecule to its neighbor are incredibly weak. When you apply heat to a covalent material like wax, the thermal energy easily overwhelms those weak intermolecular forces, allowing the molecules to detach and flow as a liquid at much lower temperatures. Thermal endurance is determined by isolation versus community. Individual covalent molecules detach easily, but dismantling the collective, interconnected grid of an ionic lattice requires devastating heat. For our final stress test, we expose these compounds to liquid solvents, comparing a non-polar solvent like kerosene to a highly polar one like water. If you drop a salt crystal into kerosene, nothing happens. The kerosene molecules lack the electrical polarity needed to interact with the highly charged ionic grid, leaving the compound intact. Water, however, is polar. It has positive and negative ends. Through a process called ion-dipole interaction, water molecules surround the individual ions in the salt, stabilize their charge, and physically pull them out of the grid until the solid dissolves. This diagram shows how we test the electrical conductivity of that newly dissolved solution using a beaker, 2 graphite rods, and a battery circuit. If we tried this test on dry, solid salt, the light bulb would remain dark. In a solid state, the charged particles are locked tightly in place, making the lattice a strong electrical insulator. But in this liquid state, the bulb is fully lit. Once the lattice is dissolved in water or melted down by heat, the ions are no longer trapped. They move freely through the liquid, transforming into perfect vehicles that carry an electrical current from one rod to the other. Electrical conductivity depends entirely on mobility. A material only acts as a conductor when its charged particles possess the physical freedom to travel through space. Over these 3 stress tests, a clear pattern emerges. A material's reaction to crushing pressure, extreme heat, and electrical current is entirely predetermined by how its atoms bond. The macroscopic phenomena we experience daily, the hardness of a rock, the melting of ice, the flow of an electrical current, are merely symptoms of the invisible behavior of subatomic particles. We rely on rigid, permanent ionic architectures to flavor our food and construct our batteries, while we depend on flexible, discrete covalent structures to build the delicate biological tissues of our own bodies. These chemical bonds serve as a definitive structural rulebook, engineering the subatomic blueprint of the entire universe into the physical reality we inhabit.